All right, in this video, I'm going to begin talking about properties of solutions. The first topic will be liquid mixtures. All right, so we already talked about the chemical potential in an ideal solution in section 5a, and I'm going to rewrite this formula here. So it depends on the chemical potential of species J when it's in a pure solution by itself, plus this term that depends on the mole fraction of J in the solution. So we've seen this equation before, and this is the chemical potential of species J when it's in an ideal solution. And remember, an ideal solution is one that obeys Raoult's law. Okay, so now we're going to calculate the mixing Gibbs energy, the Gibbs energy of mixing. And we're going to do it in the same way as we did gases in the previous section. So we start with the Gibbs energy initially, which that's before mixing. And these quantities are starred because this is two pure substances. They haven't been mixed yet. After mixing, the new Gibbs energy, we're going to have to replace this. This is no longer a pure substance. It's now in a solution. So we're going to use this formula here to replace mu A and mu B. So it'll look like Na mu A star plus RT ln XA, and same thing for NB and mu B. Okay, and now we're going to take the difference. This is exactly what we did for gases. So now the delta G, G final minus G initial, and we can see that G final, I have an Na mu A star term and an NB mu B star term. And I'm subtracting from G final Gi, which has an Na mu A plus NB mu B star. So we can see that this term is going to cancel with this term, and this term is going to cancel with this term. And what we'll be left with are just the RT ln terms. So I'll have Na RT ln XA. Okay. Now I'm going to substitute the mole fraction into this. And remember, mole fraction is defined. So the mole fraction of A is the number of moles of A divided by the total number of moles in, which I can rearrange to replace this Na. So this means that Na is XAN. The number of moles of A is the total number of moles times the fraction of those that are A. So I'm going to use this in here, and then I'm going to use the same one for NB over here. All right, so I'm substituting this here and this here. And you see when I do that, I'm going to have an N term or an N component in each term as well as an RT. So I'm going to go ahead and factor that out right now. So I get nRT times XA ln XA plus XB ln XB. And so this is the Gibbs mixing, the Gibbs energy of mixing for an ideal solution. All right, now let's find the entropy of mixing. So remember, the entropy is related to the Gibbs energy with this formula. The entropy is equal to negative dg dt at constant P. So this means that delta S is going to be d delta G dt over P. And I've argued for this before. You can imagine if I do an S initial and G initial equation and an S final and a G final equation, I subtract those two equations, I'll get this equation. Now I know delta mix G is right here, and so I need to take the derivative of that with respect to T, and that's just effectively going to drop the T off. And so I end up with NR. Oh, and there's a minus sign in front of this because of this minus sign here. Okay, so there's our entropy of mixing for an ideal solution. Next, we'll talk about the enthalpy of mixing. So enthalpy, remember, is defined as G plus Ts. So the enthalpy of mixing will be delta H is equal to delta G plus T delta S. And if we look up here, I have the only difference between the delta G and delta S is that this one has a temperature, and this one does not, and this one's negative. If I multiply this delta S by T, now I've got negative nRT, and I'm adding to that positive nRT with the same thing in parentheses here, so we can see that this is 0. And this is exactly as it was with gases. So all of these equations that I've written down here were the same as the ones that we wrote for gases, for perfect gases. And so that means the conclusions that we drew for perfect gases in section 5a also hold for ideal solutions. Okay, and then we can talk about the delta mix for the molar volume. So remember that volume is related to G as dg dp at constant T. And so that means that delta mix V is the derivative of delta mix G. Same argument as before. I take an equation for V initial, an equation for V final, and G initial, G final. Subtract the two, I get this equation. And if we glance back real quick at delta mix G that's here, we can see that there is no P in this equation. So this derivative is equal to 0. All right, now let's talk briefly about what the difference is between a perfect gas and an ideal solution. So a perfect gas, as we defined it before, back in chapter 1, there are no interactions between the particles, except during brief collisions. That's the perfect gas assumption. In an ideal solution, which is what we're talking about now, there are interactions between particles. So there are interactions. But the ideal approximation assumes that we have the same average energy for each interaction. Meaning if species A interacts with species A, it'll have about the same energy as species A interacting with species B and B with B. But interactions, but with the same average energy for each interaction type. Since it's a binary mixture, we have 3 interaction types, AA, AB, and BB. So this is a good time to point out what is the difference between perfect and ideal. Often we say ideal gas, but in this textbook and in this class, we've been using perfect gas versus ideal, which we just saw in solutions. So now we have some idea of what the differences are. So ideal effectively means that all the interactions have the same average energy. And perfect means that it is ideal, all interactions have the same average energy, and that energy is 0. So perfect is a special case of ideal. Okay, as I mentioned just a little while ago, in 5A, we talked about what is an ideal solution. And an ideal solution is one that obeys Raoult's law. And we saw in the previous section that benzene and methylbenzene obey Raoult's law really well. So benzene and methylbenzene is a good real-world example of an ideal solution. So let's take a look at that. All right, so what happens if we mix 1 mole of benzene liquid with 2 moles of methylbenzene liquid? All right, so what are the mole fractions here? So for benzene, I'll call it XB, and for methylbenzene, I'll call it XM. And mole fraction, of course, is the number of moles divided by the total number of moles. Total number of moles here is 3, so XB is 1/3, XM is 2/3, which is another way of saying this is that benzene makes up 1/3 of the molecules present, and methylbenzene makes up the other 2/3 of the molecules present in the solution. All right, now let's calculate delta G, delta S, and delta H for this mixture. And let's assume the mixture is at a temperature of 25 Celsius. So I can go ahead and calculate RT right now. R times T comes out to be 2,478 joules per mole, or about 2.48 kilojoules per mole. All right, now let's find delta G. And actually what I'd like to do is I'd like to do the molar Gibbs energy. So that's going to be delta G over the number of moles, delta G per mole. And so we go back to our equation. We want delta G over N, so that's going to cancel this N, and we're left with the remainder, RT times these terms. And so plugging in numbers, RT we calculated was 2.48 kilojoules per mole. XA was 1/3. Oh, I called them A and B. Up here I called them B and M. I should fix that. So this is for benzene, and this is for methylbenzene. Okay, so 1/3 ln 1/3 plus 2/3 ln 2/3. All right, putting this into a calculator, we get negative 1.58 kilojoules per mole. And the fact that delta G here is negative implies that the mixing of these two liquids is spontaneous. All right, now let's calculate the molar entropy of mixing. Looking back here at our formula, the molar version is going to cancel this N like we had before, so it's just going to be negative R times those familiar terms. All right, and then plugging in numbers, 8.314 for R, 1/3, 1/3, 2/3, 2/3. We end up with a positive 5.29 kilojoules per mole. And this positive is expected. Because as we discussed with perfect gases, and is also now true with ideal solutions, the increase in entropy is what drives the mixing. All right, and then the enthalpy of mixing, molar enthalpy of mixing, is going to be 0 because delta mix H is 0 for an ideal solution. All right, now let's talk about non-ideal solutions. So delta H is 0 for perfect gases and for ideal solutions, but it's not necessarily 0 for non-ideal mixtures. And similarly, delta G can be positive. And delta S, the entropy, can decrease. So what do these two things imply? Well, if delta G is positive, that means that the liquids do not mix spontaneously. In fact, they spontaneously separate. So the liquids separate, and we call them immiscible. Or at least we can call them partially miscible, depending on the degree to which they separate and mix. How can delta S be negative? How can the entropy go down when you mix two liquids? And what could happen is that some molecules, maybe AA, maybe A likes A or A likes B, some molecules might clump together, and that creates more organization in the mixture than it being purely random. Okay, so not every solution is ideal. Let's start to quantify this. And we're going to quantify this with something called an excess function. And this basically tells us how much does it depart from ideal behavior. All right, so for some variable x, some thermodynamic variable x, the excess function, the excess in this variable x, is going to be equal to the actual delta x minus the ideal delta x. Okay, a very simple way of quantifying the departure from ideal behavior. Okay, so let me show you a few examples. So let's say the thermodynamic variable is S. So for S, the excess entropy is the actual mixing entropy minus the ideal. And this is the quantity we just computed earlier that we've been using in this section and in the previous section, this quantity. So this could be calculated as the actual mixing minus a negative NR, so plus NR. This is the ideal entropy of mixing. Another example is our variable could be enthalpy. So the excess enthalpy can be the actual enthalpy of mixing minus the ideal. And we saw earlier that for ideal mixtures, this is equal to 0. So the excess is actually just equal to the mixing enthalpy itself. And another example that's similar is the excess volume is just the delta mix volume, because in the ideal situation, delta mix volume is 0. So now let's talk about a non-ideal mixture. Let's talk about a benzene and cyclohexane mixture. And for this one, what I'm going to do is I'm going to plot some experimental data. This is plotted in your textbook as well. On the horizontal axis, I'm going to put the mole fraction of benzene, which varies from 0 to 1. And on the vertical axis, I'm going to put the excess enthalpy. So remember, this would be 0 if it was an ideal solution. And we'll see here that the data shows that it is not 0. And I'm actually going to make this the molar enthalpy. So this is going to be in joules per mole on the vertical axis. And the curve fit of the experimental data looks basically like a parabola. And this is about 400, is about halfway. And this peak is at about 700 joules per mole. Okay, so let's make a few observations here. First of all, this mixing of these two is endothermic. And why is that? That's because delta H greater than 0 implies endothermic. Talked about that in a previous chapter. Okay, and that's the definition of endothermic. Okay. And HE, which is what we plotted on the vertical axis, is equal to delta H. So if HE is greater than 0, then delta H is greater than 0, and therefore it's endothermic. Okay, we're going to come back to this solution in a minute with the benzene and cyclohexane. Next, I want to define a regular solution, which is a special case of a non-ideal solution. And a regular solution is one in which HE is not 0, because it's not ideal, but the excess entropy is 0. So it behaves partially ideally. It mixes in the same way, but the enthalpy is not 0. Okay, so let's suppose that this excess enthalpy depends on composition. So this is just a hypothesis, an educated guess. But let's suppose that it depends on composition and see what happens. A sample equation for H that depends on the composition, well, it makes sense that it would depend on X and B, XA and XB. And we'll put an nRT in here and a dimensionless parameter, C. So we see that with this, again, this is a guess at what the excess enthalpy might look like. We see that the way we formulated it here, if this dimensionless parameter is 0, then HE is 0, and we're at ideal behavior. Okay, so we're going to be interested next primarily in cases where C is not 0. Okay, so to say that one more way, C is a parameter, it's an input to our model here that quantifies how much we are departing from ideal behavior. Okay, so now I'm going to make a plot of this model for HE versus XA for different values of the parameter C. Okay, so when C is 0, we get that the excess enthalpy is 0 as expected for an ideal solution. And as C increases, we get these parabolas that are taller. If C is negative, we get these inverted versions of the parabolas. So as we pointed out a minute ago, if the excess enthalpy is positive, then that means the enthalpy of mixing is positive, because those two things are equal. Which means that if we're positive here, it's endothermic. Okay, so I just mentioned that C equals 0 is ideal solution. If C is greater than 0, then we get endothermic mixing. And by the same logic, if C is less than 0, negative, you see that delta mix of enthalpy is negative, and so that implies exothermic mixing. Okay, so now let's take a look at the Gibbs energy of mixing for these non-ideal solutions, these regular solutions, as we call them. So recall that the definition of G is H minus Ts. And so from there, we can write that delta G is equal to delta H minus T delta S. And as we pointed out, delta mix H is not 0, is HE. So what about delta mix S over here? So remember, we're talking about a regular solution, which we defined as one that has no excess entropy when it mixes, okay? So this implies that SE, which is 0, which also equals the actual delta S minus the ideal delta S. So if I plug in our ideal delta S, it was negative in R, so I'm going to get plus in R. All right, and then I can solve this for delta S. By subtracting this over, so the minus sign comes back. So saying that the excess entropy is 0 is the same thing as saying that the entropy of mixing is equal to the ideal entropy of mixing. Okay, so at the left minimum, XA is equal to X1, and at the right minimum, XA is equal to X2. So the left minimum, XA is equal to X1. So what is XB? Well, this is a binary mixture, so if this is XA, then XB is 1 minus XA, which is 1 minus X1, which is X2, because it's symmetric. Our plot is symmetric. These two dips happen symmetrically around X equals a half. So however far this minimum is from 0 equals the distance of this minimum from 1. Okay, so that's what I'm writing right here. And then the right minimum is the one where XA equals X2. So then XB equals 1 minus X2, which is X1. So what are these two phases that we end up with at the two minimum? One of them is where XA is equal to X1 and XB is equal to X2. And the other is when XA is equal to X2 and XB is equal to X1. So notice that these two phases are still mixtures themselves, but they have flipped the mole fractions. All right, so I want to finish this video with an example. Let's talk about what value of this parameter C does a good job of modeling a mixture of benzene and cyclohexane, which, as I pointed out, is not an ideal solution, at 25 degrees Celsius. So for that, we're going to go back to the experimental data that I plotted a while back for this mixture. And I'm going to pick the maximum value here. And this is symmetric curve, so this maximum occurs at a half. So when it's a 50-50 mixture of the two. And it's roughly 700 joules per mole. So I'm going to use that information. So the experimental data tells us that I'm going to call these XB for benzene and XC for cyclohexane are each a half. And in that case, the excess enthalpy, which remember is molar, it's per mole, is roughly 700 joules per mole. All right, using this and our definition of H, I can find a value for C. So remember our model for the excess enthalpy. In this case, I'm dividing it by the number of moles. So I end up with this. And now I can solve this for C because I know all the other values. So C is HME, which was 700, over RT XAXB. So plugging these numbers in. T, we said, was 25, so 298 Kelvin. Which you see, we'll cancel this Kelvin. I'll have joules per mole and joules per mole, which is good because C should be dimensionless. And then I have two more numbers, dimensionless numbers here on the bottom, XA and XB, which are each a half. Okay, so plugging all this into a calculator, we get a C of about 1.13. So based on this experimental data, we could model this non-ideal solution using this dimensionless parameter for C. Now, while we're at it, let's go ahead and calculate the Gibbs energy of mixing. And we'll do the molar version per mole. So that's equal to the factor of n cancels. So that equals this. And notice this term, RT, C, XA, XB. So this one was the one that we chose C so that this term would equal 700, the experimental value that we got from the data. So we have 700, that's the first term, 700 joules per mole, plus, and then RT times this, and RT times that. All right, so there's RT, and then XA, and I'm sorry, these should be XB and XC. I did it again. XB, X benzene, cyclohexane, benzene, cyclohexane. All right, so XB and XC were each a half. So this is 1/2 ln a half plus 1/2 ln a half, which adds up to ln a half. And we plug these numbers in, and we get negative 1.01 times 10 to the 3 joules per mole, or negative 1.01 kilojoules per mole.